So yeah, we started talking about two systematic ways of solving like circuits. We started talking about like one method that was based on like KCL. We said we're going to talk about like one method that's based off like KVL, which is something that we're going to do next lecture. We said the systematic way of like doing basically solving for anything in the circuit. One way is like nodal analysis. And nodal analysis was a way to write KCL for every single node that we had in the circuit. And then we represented like everything in terms of like matrices, and then we could solve for like node voltages. One thing that was important was even though we were writing KCLs, we were solving for node voltages. We did like a few examples. Today we're going to do a few more examples. We're going to see like where we can run into like issues and how we can get around those issues. Okay. Let's do a quick review, which tells us if we have like a resistance with value R, and if we call voltage here V1, voltage at this node V2, let's just say voltage across the resistance is VR, current through it as IR. We know Ohm's law holds, so VR is R times I. But given this configuration, we know VR is nothing but V1 minus V2. So we know VR as V1 minus V2. If we combine these two, we can compute I in terms of like node voltages, which is V1 minus V2 divided by R. And this was the base of like writing the KCL for every single node. We said if IR is going this direction, if I call this I prime of R, we know I prime of R is negative of IR, right? Which is negative V1 minus V2 divided by R, which is the same as V2 minus V1 divided by R, right? So we had two separate definitions of like KCLs. The first definition was whatever current that's going in should be the same as like whatever current that's going out. And the equivalent definition was if I look at the algebraic sum of all currents, that should be 0. And we had our like convention. If it's going in, it's basically positive. It's going out, it's negative, or vice versa, right? If we wanted to go based off that definition, the second definition, if this is a direction that's going in, this would be the direction that's going out. So for the direction that's going in, I have V1 minus V2 divided by R. For the one that's going out is V2 minus V1 divided by R. Basically, I have to take into account the sign, right? And then I could just write as like algebraic sum of like all these currents and say that's equal to 0. Or we can just say like whatever current that I have going in should be the same as whatever current that I have going out. Keep that in mind. Any question on this before I move on and do one example? All right, cool. So example. Let's just say I'm given a circuit that looks like this. There's a 2K here. It's followed by a source with value for 24 volts. Another resistance in the middle. One over here as well. Followed by a 3 milliamps current source. Another current source with 1K resistance here. And a 12 volts source over here, right? And the question is asking me what is node voltages, right? Because as soon as I know like node voltages, I know everything in this circuit, right? I know current through like elements, I know power, I know everything, right? So let's just solve for like node voltages. Since it's asking for node voltages, we got to do nodal analysis, right? So let's go through the steps. What was the first step for nodal analysis? We have to choose a reference or choose a ground, right? I'm going to choose this one down here, right? Again, it's completely up to me. I can choose like the one in the middle, right? I chose the one down there. What does that mean? It means if I look at this node over here, which is exactly the same as this node, which is exactly the same as this node, they all got the voltage 0. That was the definition of a reference, right? What was the second step? To label the nodes. We have to like name the nodes. Do you agree this one up here is one node? Yeah, it is. It is different than this ground, so we call it one node. How about this guy? Is this one a node? That's exactly V1. It's not a new node. How about this guy? Is this one a new node? Still V1. How about this? Is it a new node? It is. It is different than V1 because I have this element in between, so there's a voltage drop there. So let's just call it V2. How about this one in the middle? It is a new node because it's different than V2 because of this element. It's different than V1 because of this element. So it's V3. How about this guy? It is, again, another node. Let's just call it V4. Do I have any other node in this circuit that I haven't labeled? No, I accounted for everything. What is the third step? To write KCL for every single node that we have, right? Let's start at node 1. Look at this node. Can I write a KCL at this node? Can I? I cannot. Why? Because I don't know current here. There's a voltage source there. There's no way for me I know what the current is. I can compute it, but at the moment I don't know what it is. I just know voltage across it. I don't know current through it. So I cannot write a KCL at that node. So let's just table that for a second and move on to the second node. How about second node? Can I write a KCL at second node? Yeah, it's just a bunch of resistors. I can basically assign a direction and write the KCL. I'm going to assign upwards directions. Again, completely up to me. You can choose everything is going in. You can choose like half of it going in, half of it going out. But as soon as you decide what direction you want, you have to stick to it. I chose everything upward, right? So let's just write KCL at node 2. What do I have? What is this current? That is V2 minus V1 divided by 2K. What is this current? It is V2 minus V3 divided by 0.5, right? And what is this current? It is V2 minus 0 divided by 2K. And that should be 0 because there is no inward current, right? I can simplify this. I can multiply everything by 2, right? I can simplify it, and the equation I get would be minus V1 plus 6 times V2 minus 4 times V3. That should be 0. Let's just call this equation 1. Right? Simplification is like very easy. I just need to multiply everything by 2, like I said. Right? It's not very difficult. How about at node 3? Can I write a KCL at node 3? With the exact same reason that I couldn't write the KCL at node 1, I cannot write the KCL at node 3 because I still don't know current through here. How about node 4? Can I write a KCL at node 4? I cannot because I still don't know current here, but I claim I don't really need it because I know exactly what V4 is. I know V4 minus 0 should be 12. right? So let's just sum it up and see what we have. If I look at this source over here, there is no way for me I could write a KCL. If I wanted to write a KCL at this node, I didn't have to. I knew exactly what V4 was. What is the common denominator here? The common denominator is that voltage source, right? So when I'm doing node analysis, voltage sources are either super easy, like this one, which I know exactly like what the node voltage is, or they're problematic, just like here. When are they easy? They're easy when they're located between one node and the reference. They're problematic when they're located between two nodes that are not reference. So let's just make that remark, just make sure that we know exactly what's happening. Remark. Doing nodal analysis, voltage sources are either one, easy, super easy, which we know that's the case when they are between one node and a reference. Or they're problematic, which again, we know that's the case when they're between two nodes, right? Over here. What if there was a way that I could get around this problematic source? What if I basically combine these two nodes into one and write the KCL for that node? I can do that. Why? Because let's just assume there is an I going through here. Let's just call it I going down, right? If I write the KCL at this node, it's going to be this current, and this current going down. If I write a KCL for this node, it's going to be this current, and this one that's going into it. So for this one, it's going out. For this one, it's going in. If I add up these two KCLs, I end up with like one KCL. But what's happening is that since one I is going out, the other one is going in, one of them has positive sign, the other one has negative sign, they cancel out. Right? So instead of looking at like two nodes, I'm going to combine them. And I'm going to name this guy as a supernode. Now if I write the KCL for this supernode, I don't have any issues with this source. So the solution to this guy, solution is supernode. Right? So let's just write the KCL for that node. If I look at it, I already have this direction. I have this direction for this one as well. I don't have anything for here. I'm going to assume it's going out. And then I have every other directions. So let's just write the KCL for supernode. Again, definition of a KCL remains the same. Definition of a KCL tells me whatever current that's going in should be the same as whatever current that's going out. Right? Again, the reason for it is that if I only wrote it for K1, the definition of a KCL basically holds. If I only wrote it for KV3, again, the definition holds. But if I add these two things up, since the current through that source, for one of them is going down, for the other one is going up, they cancel out. They're opposite directions. Right? And that's why I can write it for this supernode. So what is the KCL for this node? again, whatever current that's going in should be the same as like whatever current that's going out. What is the current that's going in? Well, this one is going in. Again, I look at the whole thing over here as a giant node, right? So this one is going in. So what do I have? I have V2 minus V1 divided by 2K. What else is going in? This one is going in, right? So I have plus V2 minus V3 divided by 0.5. Do I have anything else that's going in? Well, look at it. The whole thing is here, my node. This is going in, this is going in, this goes out, and this one goes out. So I have nothing else that's going in. So that equals to whatever that's going out. Well, this is going out, so I have 5 milliamps. This one's going out, so I have 3 milliamps. And I have this current going out, which is going to be V3 minus V4 divided by 1K. Right? Multiply everything by 2, simplify it. The equation you get would be V1 minus 5V2 plus 6V3 minus 2V4 equals minus 60. Now let's call it equation 2. Right? And I already know V4, right? We said V4 is the easy one because it's located between one node and the ground. So V4 is basically 12. We know it. But look what we did. Because we combined V1 and V3 into one node, and we wrote the KCL for that giant node, we're missing one equation. I have 4 unknowns, but I have 3 equations. What can I do? I'm going to go back to that supernode that I have. If you look at that supernode, I haven't utilized the information that supernode is giving me. That supernode basically tells me if I look at V1 and V3, I know the potential difference between those 2 nodes. Right? What is the potential difference? What is V1 minus V3? Is it 24 or negative 24? It's negative 24 because we hit the negative sign first. Right? So information from supernode tells us I have V1 minus V3 equals minus 24 volts. And again, I'll call this equation 3. And obviously, equation 4 is V4 equals 12. Right? Right? I have 4 equations, 4 unknown. I can put in terms of like a matrix and solve for it. Let's do it quickly. I have my coefficient matrix times my unknown voltages, known variables, and that should be a constant. Looking at the first equation, that tells me minus V1 plus 6V2 minus 4V3, that should be 0. So it is minus 1, 6V2 minus 4V3 times 0V4, that should be 0. Right? Equation 2 tells me 1 times V1 minus 5 times V2 plus 6 times V3 minus 2 times V4, that should be negative 16. Equation 3 is 1 times V1 plus 0 times V2 minus 1 times V3 plus 0 times V4, that should be negative 24. So I have 1, 0, negative 1, 0, that should be negative 24. And the last equation tells me 0 times I1 plus 0 times V1 plus 0 times V2 plus 0 times V3 plus 1 times V4, that should be 12. So that is 0, 0, 0, 1, and that should be 2. Right? Now this is my coefficient matrix A. This is my unknown variable x, and this is my known vector. I can find x, which is v1, v2, v3, v4, using A inverse. Right? If I give it to like your calculator, it turns out v1 is minus 19.76 volts. v2 is minus 0.471 volt. v3 is 4.235. And obviously v4 is 12. Right? Keep that in mind. This matrix over here is just a coefficient. Right? So let's recap what we have. We still have KCL at every single node that we have. However, when I'm doing node analysis, voltage sources are either super easy or problematic. They're easy if they're located between a node and a reference, because that tells me exactly what the node voltage is. They're problematic when they're located between 2 nodes that are not reference. Right? What is the idea? If they're problematic, well, we have to get around them. And the idea is that we have to write the KCL for this supernode. Right? Because doing supernode removes one node, we're going to miss one equation. So we're going to have to go back to the supernode and utilize the information that's given us. In this case, the information was, where did it go? The information was v1 minus v3 equals minus 20. Right? Does that make sense what's happening? Is that clear? This is basically a type of like node analysis you probably get on the exam, by the way. Okay? Yes.
Exam, like for the matrices part, like we just be able to plug it into the calculator. And
yes. Yes. On the exam, I'm not going to give you like 4 by 4 matrix. It's probably like 3 by 3. So you can actually, if you don't have like a calculator, you can still like solve it. Right? And on top of that, I don't really care about like final answer as long as you know how to solve the problem. Now I know everything in the circuit. I can basically compute whatever the question is asking me. For example, if I ask you what is voltage across this, what is it? What is voltage across the 3 milliamps source? That's V3, right? It's V3 minus 0. So I'm going to go back to this guy and say, oh, it's 4.235. Right? If I ask you what is current through this guy, what is it? It's V2 minus V3 divided by 0.5. Right? And I know everything in there. So as soon as I know the node voltages, I know everything in the circuit. Okay? Any question? Let's do one more example. Let's just say I am given this circuit. Voltage across this is Vx. It's a 1K, followed by another 1K. I have a 2 milliamps, a 2K, a dependent source with value 2Vx divided by 1,000, and a 1K resistance. And the question is asking me, what is V out? Right? Look at a circuit. I still can do node analysis. There is nothing wrong with like node analysis. The only thing I observe in this circuit is that there is a dependent source there. right? But we know how to handle a dependent source. How? We're going to treat it exactly like an independent source. The only difference is that, like, I got to know the value of that source. So I got to somehow compute Vx separately, right? So let's do it. What is the first step? Choose a reference. I'm going to choose the one down here as my reference. What it basically means is that voltage here is the same as voltage here, is the same as voltage here, is the same as voltage here, and they're all 0. Right? That's what we know. What is the second step? Label them. Label the nodes. Do you agree this one up here is one node? Do you agree with me? That's different than my source. How about this guy? Is this a separate node? Is it? It is. Let's just call it V2. How about this guy? Is it a separate node? No, it's exactly V2. How about this guy? It is, right? Let's call this node Vx. Why? Because the question already told me voltage across this guy is Vx. And since it's between like this and this reference, it is exactly Vx, right? If you remember when I was telling you about node analysis, there was an intermediate step that we said if we could like simplify it, let's just simplify it. I'm not going to do that here. Why? Because look, I have a dependent source, and the value of this dependent source depends on this Vx. So if I simplify it, I'm going to lose that Vx, right? So I'm going to keep it. But what I'm claiming is that I can write voltage across that 1K. Basically, I can write this Vx in terms of V1. And if I can do that, I can basically get rid of it. But how? Is that thing familiar to us? Let me rephrase it. I know voltage here across this guy is V1, right? It's V1 minus 0. Therefore, voltage across these two elements is also V1. Then what is Vx? What kind of circuit is that? It's a voltage divider. Remember like what voltage divider was saying? Voltage divider was telling us if I have like a source Vs followed by R1 and R2, then voltage across R2 is R1 divided by R1 plus R2 times Vs. So what it tells me is that voltage across R1 and R2 is Vs. And then I can find voltage across R2 in terms of voltage across both of them. That's exactly what it says over here. It tells me voltage across these two is V1, which is V1, because voltage across here is V1, and this is no different than this guy, therefore voltage from here to here is V1, right? If voltage from here to here is V1, what is Vx? So Vx is 1K divided by 1K plus 1K times V1, which is V1 divided by 2. Now I have everything in terms of V1, right? Let's write KCL. Let's just write KCL at node 1. Since I know exactly like what Vx is in terms of V1, now I can combine these two, right? I can combine them and write 1 plus 1, which is a 2K, right? Now I don't really need the information of Vx. I know it in terms of V1, right? What is KCL at node 1? Again, I'm going to assume this is going out and this is going out. My assumption. What is KCL at node 1? It's V1 minus 0 divided by 2K right? It's V1 minus 0 divided by 2K. This one is still like going out, so it's V1 minus V2 again divided by 2K. And that should be the same amount as whatever that's going in, which is 2 milliamps. Right? How about KCL on node 2? What is it? I already decided on the direction here, so I cannot change it. But I haven't decided on this one. So let's assume this one is going out as well. Whatever current that's going in should be the same as whatever that's going out. So I have this one going in, so it's V1 minus V2 divided by 2K. This one is also going in, so I'm going to write it as 2 divided by 1K times Vx. I wrote 1,000 as like 1K, right? And that should be the same amount as like whatever that's going out, which is V2 minus 0 divided by 1K. Right? But if you look at the bottom equation here, I have a Vx. So I have 2 equations, 3 unknown. But I already calculated Vx in terms of V1. Right? So I'm going to plug it back in here. So I know this guy is V1 over 2. Now I have 2 equations, 2 unknown. I can solve for V1 and V2. It turns out if I solve for it, V1 equals V2 equals 4 volts. What is V out then? What is V out? What is it? V out is voltage across at 1K. What is it equal to? It's V2. It's exactly V2. Right? Because remember, V2 is over here as well. And voltage across this is V2 minus 0. So V out is exactly V2, which is 4 volts. Right? Does that make sense what's happening here? Is that clear why V out is V2? Remember, this one over here, we called it V2. And this is exactly the same as this V2. So if I wanted to find voltage across this, that's V2 minus whatever voltage that's down here. But down here is nothing but the reference. So the voltage here is 0. So I have V2 minus 0, which is exactly this V out. Right? So the whole idea here is that if I have a dependent source in the circuit, I'm still going to treat it just like an independent source. The only thing that's different here is that the value of that dependent source depends on something else in the circuit. So I have to somehow compute it. In this case, Vx was voltage across this one. I could compute it in terms of my node voltages just by observing that voltage from here to here is V1. Therefore, voltage from here to here is also V1. If I have 2 resistors back to back, I know voltage across them. I know voltage across every single one of them. How? Through voltage divider. Right? So that's basically how I wrote Vx in terms of my node voltages. Right? Is that clear to everybody? Yes? No? Voice contact? No? All right. So let's move on and do one more example. This example is quite difficult. Not really, but more difficult than like whatever we talked about so far. So let's just say I have a circuit that looks like this. I have a 2K resistance here. I have a source, positive, negative. Negative is down there. 6 volts. I have a current source, 4 milliamps. I have a 1K. I have a 2K. This is connected to like another 1K, another 2 milliamps, a voltage source, negative, positive, 12 volts, and 2 1Ks. Right? And again, let's just say we want to find node voltages. Right? If I know node voltages, I know everything in the circuit. What do? Again, we're going to go through our recipe. That recipe holds for everything. What I have here is a circuit. I want to do node analysis. The first step is choose a reference. I'm going to choose like the one on the bottom. Right? Again, up to me. I can choose whatever I want. I choose this one. Therefore, what I'm saying is that voltage here is the same as voltage here, is the same as voltage here, is the same as voltage here, and they're all 0. Right? What is the second step? Label them, name them. Do you agree this one up here is a node? That is a node. Indeed, that is a node. That's not the reference. How about this guy? Is this guy a new node? It's exactly the same as V1 because there's no potential difference here. How about this guy? Is this a new node? Still no, right? Because there is a wire there. How about this guy? Still V1. There's no difference. How about this guy? Is this a new one? It is a new one because there is a potential difference between V1 and this node. How about this guy? Still a new node, right? V3. This is a new node, V4. That's the new one, V5. Right? That's all the nodes I have in this circuit. I got nothing else. Right? Third step tells me I have to write KCL for every single node I have. Let's start at node 1. Can I write a KCL at this node? No. I have a voltage source that's between these two. That's a problematic one. Let's move on to the second node. So KCL at node 2. Can I write a KCL at node 2? Yeah, I know currents through every single one of them. So let's just assume everything is going out. Again, my assumption. Okay? So what do I have? I know whatever current that's going in should be the same as whatever current that's going out. So what is current here? That's V2 minus 0 divided by 2K. The current over here is V2 minus V1 divided by 2K. Right? That's this current. And then that should be the same amount as the current that's going in, which is 4 milliamps. Right? Let's call this equation. Can I write a KCL at node 3? With the exact same reason as like V1, I cannot write a KCL at this node. Let's move on to V4. Can I write a KCL at this node? Again, I can't because I don't know current here. How about here? Still no. So what was the idea? Since these voltage sources are located between two nodes that are not reference, the idea is that like we have to glue them together and form a supernode. So let's call this over here supernode 1, and this one over here supernode 2. Right? Let's just write a KCL for supernode 1. Again, KCL holds. What means is that whatever current that's going in should be the exact same as the current that's going out. So let's do that. Well, I already know the current through these two. I don't know this one here. I'm going to assume it's going out. Okay. What is this current? Well, this current is going in. Let's just look at like going ins. So what is the current here that's going into the supernode? That's V2 minus V1 divided by 2K. What else is going in here? What else is going into this guy? Is there anything else? There is. This guy. Remember, this is still V1. This is still V1. This is still V1. So that is part of this supernode. So I have this 2 milliamps going in. So I have plus 2 milliamps. Do I have anything else that's going in? No. So that should be the same as whatever current that's going out. Let's see what's going on. First of all, this is going out. This 4 milliamps. What else is going on? This guy. This guy's going up. What is the current here? It's V3 minus 0 divided by 1K. What else is going out? Is there anything else that's going out? Yeah, this guy right here. Remember, this is still a part of the supernode, right? So I have plus V1 minus V4 divided by 1K. Right? Yes. Again, that's my choice. Yeah, you could just say it's going up. Right? So let's call this equation 2. Again, since I basically combined these two together, I'm losing information. So let's just employ whatever that thing says. What is it telling us? So the information for supernode 1, what does it tell us? It tells me like V1 is 6 volts higher than V2, than V3. Right? So V1 minus V3 should be 6 volts. Right? I'll call this equation 3. Right? Let's move on to the supernode 2. I have to write KCL at supernode 2. What do I have? Again, whatever current that's going in should be the same as whatever current that's going out. I don't have any directions for these two. I'm going to make assumption. So I'm going to assume these two are going out as well. I cannot change the direction for this guy because I already set it. Right? So what do we have that's going in? Do I have anything that's going in? Well, I have this one, right? So what is it? It's V1 minus V4 divided by 1K. Do I have anything else that's going in? Remember, this whole thing is my node. Right? I got nothing else. This should be the same as whatever current that's going out. First of all, I have this 2 milliamps that's going out. I assume this one is going out, and this one is going out. What is current here? It's V4 minus 0 divided by 1K. What is current here? It's V5 minus 0 divided by 1K. Right? Let's call this equation 4. Again, we're missing one equation. And that equation can be obtained by looking at the information that the supernode has given us. Right? So supernode 2 information What does that tell me? What is the information that the supernode 2 is giving me? Yeah. It's either V4 minus V5 equals negative 12, or V5 minus V4 equals 12. Right? There it is. So I'm going to write it as V4 minus V5 equals negative 12. And this is equation 5. Right? Now I have 5 equations, 5 unknowns. I can solve for V1, V2, V3, V4, and V5. Right? So 5 equations, 5 unknowns. We can solve for V1, V2, V3, V4, and V5. And as soon as we know V1, V2, V3, V4, and V5, we know everything in this circuit, right? For example, I can ask you what is current through here. Let's just call it I. I can ask you what I is. Right? What is I? I cannot write it in terms of Ohm's law. What I can do is I can write a KCL at this point. Now I know this current, I know this current, and I know this current. So I can write a KCL at this node and get I. Right? So for instance, we can get I by writing a KCL at node 1. But this time, the difference is I know this current, which is V2 minus V1 divided by 2K. I know this current, which is V1 minus V4 divided by 1K. And I know this current that's going in, which is 2 milliamps. Right? So I can write a KCL at this node and find I. Right? I can also ask you what is voltage across this 1K. What is it? What is voltage across 1K? That's just V3. Right? It's V3 minus 0. Right? So as long as I know V1 through V5, I know everything in this circuit. Right? So what we learned today was that we can do KVL and KCL always, but we have a systematic way to solve the circuit, which is nodal analysis, which utilizes KCL. What we learned was if we have voltage sources can be either very easy or problematic. And if it's problematic, the idea is that we have to do a supernode. But as soon as we do supernode, we're losing information. So we're going to have to go back to that node and try to find the information that node has given us. Right? What we're going to be doing next lecture, we're going to start talking about mesh analysis, which is based on KVL. And then we're going to compare these two methods. And then next week, we're going to start talking about superposition and then op amps. I'll see you guys Friday.